Rebecca,
Hello.
astronomy textbooks aren't just made of trees.
Mm-hmm.
Trees are astronomy books. You could even call them astronomers. But I'm Mark Popenchok, and I'm a human astronomer.
And I'm Rebecca Rand, and I'm a science journalist. Welcome to Celestial Bodies, the podcast where we explore interactions between outer space and living things. So, go on. What's this about trees?
What if I told you that before Galileo, before Babylonians, before written language, before any human history, trees were recording stuff happening beyond our planet? Modern astronomers are now starting to use these records from the trees to tell when these events occurred. So trees are kind of like a historical record, measuring device, and living thing in one. Data, telescope astronomer, and provider of shade.
Wait, hold up. Are you one of those crazy people that says, like, trees talk to each other and they cry when they're in pain?
Yes, and I cry when they're in pain too. But look, people have been using these trees as historical records since the 1700s. Okay, if you look at a slice of a tree trunk, it's got all these rings. And trees grow a new layer each year. And how it grows tell you what happened that year. If there was extra rainfall or cold winters, it'll be reflected in the size of the tree ring.
Got it. But, rain falls from the sky, not space. So how does the tree get information from space?
Right. Well, I'll give you an example. Okay, but I have to go through medieval England to explain it. So let's paint a picture.
Okay.
Alfred the Great is writing the Anglo-Saxon Chronicle. Okay?
Uh-huh.
He's one of the Mercians, part of the kingdom in what we now would call Great Britain. But the Kentish upstarts are making a lot of ruckus around the town of Otford.
Otford.
Otford. Yes, very good.
Okay, I'm seeing it. There's a lot of big, burly men covered in dirt. They're going, rah!
Right, and they've got their mud rakes and turnip catchers, and they're going to go rough up those pesky Kentish upstarts and get all their buddies, and they have a big old fight, right? Classic good day out. But when the fighting is all done for the day, they look up and see something bizarre. They see, and I quote from the Anglo-Saxon Chronicle, this year also appeared in the heavens a red crucifix after sunset.
Of course it was a crucifix. They thought everything was a crucifix. Okay, so what actually did they see?
Okay, well, we don't know for sure. And, the thing about this chronicle is that the next line says something about wonderful serpents rolling in the hill, so we don't know how much mead was going around.
Probably a lot. I was expecting a little more science, less mead.
Mead and science do go well together.
Yeah.
Not that I know from too much experience.
So give me some science. What did they actually see?
We don't really know for sure, but it could probably be the Aurora Borealis.
The Northern Lights.
The northern lights in the sky.
So I guess someone else saw it that day and wrote about it.
Well, someone did, or should I say something.
Something?
It was a tree.
Okay.
Here's how a tree could potentially see the northern lights. Let's get into a tree's perspective. Let's be trees.
Oh, okay.
We gotta be calm, we gotta be zen, we gotta breathe. Time is different for trees. Minutes and hours don't mean as much as days and months. And our goal as a tree is each year to grow bigger, to get more sunlight.
Mm-hmm.
To do that, we need to make cells. And to do that, we need carbon. When you and I breathe as humans, we want the oxygen in the air. But trees and plants, when they breathe, they are taking in carbon dioxide to fuel their growth.
Right.
So trees are constantly just taking in whatever carbon dioxide they can. They solidify the air around them into their ancient forms, ever reaching into the sky for more light.
Wow, so poetic.
Thank you. And one day, as they're breathing, they're not really going to notice it, but the air might be a little bit heavier. Some of the carbon that they're funneling through their capillaries is just a little bit different.
Different? Different how? I mean, aren't carbon atoms just atoms?
Yeah, I mean, for all intents and purposes, every carbon atom can bond like any other. It's just some small amount, one of every trillion, is a little heavier. We call it radiocarbon. because it's slightly radioactive. And over time, that small amount decays, which basically acts like a clock.
All right, so where does radiocarbon come from?
When the Earth's upper atmosphere gets hit with radiation from space, like from a solar flare, it smacks into our atmosphere, which makes light, just like the aurora, but that also makes radiocarbon.
Wait, the aurora, that's the northern lights, right?
Right. So, along with those northern lights, the radiocarbon gets made in the upper atmosphere and then filters down from the atmosphere and around to the rest of the planet, including into living things. You, me, a tree, we're not going to notice the difference, and we're still going to use this carbon just like normal in our cells. But scientists can measure how much of this heavy carbon there is.
Wait, okay, this is ringing a bell. This sounds like what they do for radiocarbon dating.
It is exactly. Radiocarbon dating looks to see how much radiocarbon is left over after something has been dead for a while. Most living things are moving carbon around their bodies all the time, and that refreshes how much radiocarbon there is. It's only a valuable clock when it starts to decay. Once the living thing dies, no more radiocarbon gets in, and since it decays at a well-known rate, it's a clock for how much time has passed. But if it gets locked in somewhere, like in a tree ring, the amount of radiocarbon can tell you something.
Right, because in a tree, you can see the changes from year to year.
Exactly. This is the study of dendrochronology, where we look at the tree rings from one tree and line them up with another tree and line up their tree rings with another tree. And we can get this unbroken history connecting each tree ring back through thousands of years.
Damn. So we can find out like the literal year these radiation events happened.
Exactly.
So if you find extra radiocarbon in a tree around a specific ring, that means...
Great question. I know you've already asked to me once, but I talked to a guy who asks these exact same kind of questions.
I believe I'm recording now.
His name is Benjamin Pope.
I'm a lecturer in astrophysics, which is what Americans would call assistant professor, at the University of Queensland in Brisbane, the capital of the state of Queensland in Australia.
And he was part of a study that was looking at these moments in time when there was a lot more radiocarbon produced.
I read this paper by Fusa Miyake in 2012, and it blew my mind.
Miyake was measuring how much radiocarbon was in individual tree rings using that tree ring history, the dendrochronology, and counted backwards to exact years in older and older trees until...
There was this huge spike in radiocarbon in 775. And I was just fascinated. I thought, what on earth could this be?
Wait, 775, that's the date of the Anglo-Saxon battle you talked about, right?
Exactly. And 7075 is just one example. They found 6 of these events in the last 10,000 years where there was a spike of radiocarbon in the tree rings.
And all this, is it just coming from one tree?
No, it's not just one giant tree. It's actually, they've measured this for hundreds of trees. They've had to use a bunch of them from the northern, southern hemisphere, because any one tree might be able to just get a little extra radiocarbon here or there. And so they needed to average it out over hundreds of them, because radiocarbon is getting produced in the atmosphere and spreading around the world.
Wow, that's a lot of trees. So the radiocarbon in the rings, it's like a clue to what's happening in space at a specific time in history. Is it just solar flares, or what else could be causing these?
Right? Solar flares is one idea. It could be maybe a supernova or something. And Ben did a lot of research about trying to figure out what those are. But another thing about Ben
the Hittite Empire, the Korean Peninsula,
is he loves history.
the High Middle Ages, by the Uyghur Empire, or by a Manichaean monastery.
We love an interdisciplinary king.
So one of the original interests was to try and link these radiocarbon spikes with historical events, just like the 775 event connects to that line in the Anglo-Saxon Chronicle. But we already have a history matching that one up. It would also be cool for events that we don't know the exact date of.
Like what?
Well, have you heard of Leif Erikson?
Right, the Viking. So we have more big burly guys going, rah!
Yeah. One of Ben's colleagues did connect a radiocarbon spike to the Viking exploration of the Americas.
So he was able to show that it was in 1021 AD, precisely because the 993 AD Miyake event shows up in tree rings from the site.
Huh. So we know for sure that, say, this one or that one was because of a solar flare or a supernova or something. But, I mean, how would we even be able to tell?
Right. So there's a pretty regular amount of radiocarbon that gets produced just from particles from the sun hitting the atmosphere. But something extra seems to be happening in these years where there is more radiocarbon. And that's what Ben and this group was trying to figure out. They did some fancy statistics
ODE solvers, transport equations very fast, these in Python.
and learned more about the radiocarbon production rate in these individuals' years. Remember, it's getting made when radiation from space interacts with the atmosphere. Normally that's just the sun, but if it's something else, it's useful to understand how much more radiation it is.
So you get about 4 years worth of ordinary radiation dumped all at once in the 775 event.
Wow, that's a lot of radiation. So, again, does he know what caused it?
Well, yeah, I mean, that's the sort of the $1 million question.
Rebecca, we called a leading expert halfway across the world to find out, and they have the exact same question as you.
Science always does this.
We're nothing if not consistent.
The $1 million question is really, what are these events? What are their properties, but also what's their underlying physics? And that's something we've tried to address in our paper.
And that is the politest scientific way of saying he has no idea. They calculated how much radiocarbon was produced and like how long these events lasted, but there's no clear answer to what it could be causing these things to happen. But he does know how bad it would be for our technology if one of these events were to happen today.
According to one series of recent estimates, it was the 775 event was between sort of 5 or 10 up to 80 times bigger than Carrington.
Wait. I know what this is. The Carrington event was when there was a giant solar flare, which, vomited a bunch of radiation at Earth. And there was like telegraph wires, going up in flames, huge northern lights in the sky.
Bad stuff.
I mean, the northern lights are nice, but, poor telegrams.
Carrington would have been completely disastrous for the modern world, would have taken out all of our satellites and telecommunications and undersea power cables, long-distance power cables. Talking about sort of something like the Montreal 1989 solar storm taking out the Quebec power grid, times 10.
Well, that's not good.
Yeah, I know. Which is why Ben and others are really interested in studying this more.
I think this is really a topic to watch over the next couple of years because everyone is getting more data, rapidly all the time at the moment. If these are extreme solar flares that are 10 times bigger than Carrington, give or take half an order of magnitude, these are potentially civilizational risks. It would take out the power grids of essentially all high latitude countries.
And so it's definitely a bit of a scary thing to think about one of these events happening in our lifetimes.
Right. I mean, based on what we know, how likely is this compared to, say an asteroid slamming into the Earth?
It's a lot more likely than a lot of things that people have put much more effort into dealing with, like asteroid collisions or something. If these occur about once every 1,000 years, you could go, oh, well, who cares, right? 1,000 years is a long time. But they occur at random, not periodically, as far as we can tell. And so we're talking about a 1% probability per decade. And I don't know, I think a 1% probability is the sort of thing you want to insure against by having some knowledge of what the physics are.
But on the other hand, the last 10,000 years of human civilization have survived it perfectly fine.
Yeah, but that was before TikTok, Mark.
Rebecca, I think it's okay if we lose TikTok for a little bit.
I can think of one upside.
Oh?
If it knocks out the power grid, then there's no lights. And if there's no lights, you as an astronomer should know.
We can see the stars?
We can see the stars. We can see the sky. Have you ever actually seen the Aurora Borealis?
I've never seen it in real life, no.
Hold on. You have to see this video. Most videos of the Aurora Borealis, when you see them, they're moving really quickly across the sky because they have to do a time lapse. But somebody has finally been able to catch it on tape, moving in real time. And I just had no clue that it actually looked like this. I thought it was an animation.
Oh my gosh. It's just a field of green and blues and it's just floating in the sky. It's like pillars of light just hanging in space right there with the stars behind them.
I mean, maybe those are the snakes they were talking about.
Yeah, I don't see oh wow.
Wonderful serpents.
Yeah, for sure. I mean, look, that could probably be worth losing TikTok for a couple of months.
We hope you've enjoyed our podcast.
Yes, this was part of a CUNY Science Communication Fellowship. There are several other episodes throughout the summer.
I'm Rebecca Rand.
I'm Mark Poppinchuk.
And
This has been Celestial Bodies,
the podcast where we explore how space interacts with living things.